So by way of introduction then, so my name is Philip Murray. I'm the admissions tutor here in mathematics at Dundee. I'm also an advisor of studies and a senior lecturer here. So you're really very welcome to today's session. My email address is in front of you. That's an important piece of information perhaps to get from today. So it's pmurray, all lowercase, at dundee.ac.uk. So again, please just feel free to email me if you have any questions. I'm happy to help you along with those at any point, really over the admissions cycle or out with the admissions cycle. So please feel free to contact me. So yeah, you're very welcome to today's session. In normal times, we obviously have these events on campus, and lots of my colleagues, we have a very good attendance from staff, and it's a real good opportunity to come and meet lots of different staff and for us to meet prospective students. And obviously with the current situation, that's not possible. So it's a real shame that we don't get to meet you in person today, and you don't get to meet more folk in the department, but it's really just the way it is, as we all know. So moving onwards to what I'd like to speak about today, there are three main topics to think about from my perspective, and hopefully lots of time for questions from you. And those topics are firstly, well, why mathematics? So just in general, why would someone be bothered or want to study mathematics at university? And then a little bit more focus on why mathematics at Dundee. And then finally, I'd like to give you a bit of information about our programs and the kind of structure we have and the degrees we offer, and so on. And again, the Q&A function is there. It's the little icon with the question mark, I believe. What you see is slightly different to what I see, but yeah. And please feel free to ask questions. Okay, so firstly, well, why mathematics? So, of course, there are a number of reasons that one can study mathematics. Oh, before I go on, I need to just apologise in advance. Obviously, I'm working at home, and we've recently got a puppy, and I've got a 3-year-old and a 5-year-old. So if that door behind me bursts open, then I'll panic, and we'll have to have a little break. Hopefully it won't. Okay, so let's get back to business. So why mathematics? So I think one of the first reasons to study mathematics is because you enjoy it. So we're one of those subjects where most people have had a chance to sample mathematics at school and have a reasonable idea about a kind of core ideas in mathematics. And based upon that information, do you really enjoy mathematics? And that's certainly something to take account of before deciding to embark upon a 3 or 4 year undergraduate degree. Another important thing to think about is employability. And what we know is that mathematics is one of the essential transferable skills across all of science, engineering and technology. And to kind of illustrate that point, I've on the table on the bottom left here, I've highlighted some of the different sectors of the economy that we know people with mathematics degree go and work in. And you can see there, well, you can read some of them off, but finance and banking, logistics, design, insurance, etc., etc. And the key point is that there isn't really one place that mathematicians go. There's not a canonical pathway. Mathematicians can go and work across really all sectors of the economy. And how can that be? And the answer to that question is what I've just said. It's because when you do a mathematics degree, you learn a language essentially, and that mathematical language can then be applied in lots of different ways into lots of different problems. So one could use that mathematical language to study, say, in finance, the future behavior of a stock price, or one could use that mathematical language to, study cells moving around in a dish in a biological experiment. And the key idea, it's the same mathematical language that one uses, but the diversity of applications is very broad. So the third reason to think about studying mathematics, I think, which is also very important, is the bar chart on the right. So we know that mathematics is actually a relatively high earning discipline to study. So the Institute for Fiscal Studies have reported these data. They're a very well respected economic think tank. And what they did to generate these data, so there's a whole analysis they did, but this is one of the summary figures, which you can find online if you're interested. But they looked at the median salary 5 years after graduating across lots of different subject disciplines. And you can see the high earners are at the bottom. Medicine and dentistry was their top earning graduates. But you can see that mathematics is the third from the top there at the bottom of this chart. And the reason for this is, I think, largely to do with, again, the first point I made, that mathematicians go and work across these diverse areas of the economy. So lots of mathematicians go and work in finance and banking, for example, or the insurance industry or actuary, etc., etc. Okay, well, let's move onwards and try and give an example of mathematics in action. So I'm going to try and break up the slides a little bit with some diversions, really, and this is the first one. And the idea is to try and think about how we can apply mathematics for this example in the real world. So here's a little game. Suppose you were the Prime Minister of a fictitious country and there was an outbreak of a new infectious disease and cases were rising. So what should you do? And I've put some options in front of us. So you could ignore the problem, you could have a look at some data and see what you think, or you could make an immediate intervention. And I guess one can extend this list. So let's assume we're going to look at some data. Here you can see it's actually the data from last March, and this was the number of new infections of COVID-19 per day last March in England. So these are real data, but the problem I'll try and address as we go on. So suppose the data look like this. By day 10, you can see in this graph there are around 40-ish new infections per day, and it's pretty clear that the trend is increasing here, right? As time goes on, the number of new infections per day is increasing. But suppose you said, well, in a country of 50 million people, let's say, this is a very small number of measured new infections. So perhaps I'll just wait a little bit and I will see what happens. So you wait for a week, you keep measuring, and then the data look like this. So we've tagged on an extra week of data, and by the last day here, you can see it's around 250 new infections per day. And you might still say, well, this is still quite a small number. Let's wait for another week and see what happens. And after the next week, you can see that there are almost 1,000 new infections per day. And the question now is, well, what is going to happen if one tries to project into the future? And in this graph, it very neatly summarizes the problem that we all faced a year ago and are still grappling with. So the blue markers are just those data points that I showed you. It's just the number of measured new infections per day, as a time series from day 1, which was around about last March, for 24 days. And this red dashed line is a line that you don't want to cross. You don't want the blue markers to go above some threshold, which is determined by your healthcare resources mainly. And you don't want the blue markers to go above that, or that is just a situation for lots of probably fairly obvious reasons that you want to avoid. But the question is, from a kind of modelling point of view, what's going to happen in the future? So we're about day 24 here. We know that there are order 1,000 new infections per day. What's going to happen at day 40? What's going to happen at day 60? And how do you answer that question? So this is where mathematical modelling is actually very useful and has been very useful. So you can develop a mathematical model and try and use that model to project into the future and use that projection to inform perhaps your public health policy. And there's a very famous model in mathematical epidemiology called the SIOR model. So S stands for susceptible, the number of susceptible people in your population, and I stands for infected, the number of infected people, and OR is a variable that represents people who've previously been infected. So it represents people who've recovered or people who have died from the infectious disease. So the SIOR model. And the idea in the SIOR model is that people move around between these compartments in particular ways. So if you're susceptible, you can become infected, and if you're infected, you can infect susceptible people who haven't yet been infected, or you can recover and or you could die from the infectious disease. So this is a dynamical system. The number of people in the different compartments changes in time. And one can then begin to use calculus to try and describe these changes. So I'm not going to get into the details at all today, but these are differential equations in front of you in the bottom. This ds dt is the total rate of change of the number of susceptible people with respect to time. And similarly, di dt is the total rate of change of the number of infected people with respect to time. So you can use calculus to describe what these rates of change are mathematically. And then on the right-hand side, that's where your kind of model building comes in. So the ds/dt equation is one term on the right-hand side, and it just says that the rate at which you lose susceptibles in the system is proportional to the number of infected people you have. So you can see the I appearing on the right-hand side times the number of susceptible people you have. So if you had no infected people, if I was 0, then those who are susceptible would remain susceptible, right? Because they can't get infected because there are no infected people to infect them. If you had no susceptible people left, S would be 0, then obviously ds/dt would be 0. And similarly, one can kind of build a model for the other variables. And I don't want to get into the details of that today. We actually study this model at level 5 as part of our a series of lectures in mathematical epidemiology in one of our modules. So I don't want to get into all the details. But what I want to do is to think about what you can do with this model. So basically, what you're seeing in front of you now is a projection of this model. So you can, and again, I'm going to skip some details, but you can essentially make the model go through the blue dots, which are the historical data. And by that, I mean you can choose these model parameters so that historically the red line, which is the model solution, goes through the blue dots. So it kind of agrees with history. And then you can solve the equations and you can get a projection of what the future time course looks like for this infectious disease. And if you did that to the historical data in March, then you would see that you've got a huge problem, right? Because the red line, which is the future projection of the model, is going above the dashed line, which is the situation you want to avoid if you're managing a country. So this is obviously spelling something terrible, and this would motivate the need for a change in public health policy. So you need to do something, you need to change something to change the time course of this infectious disease. So again, I'm probably only going to give one of these examples actually, but you can do things then like simulate social distancing. So there's a parameter in the model that represents, at least partially, how much people are moving around in the population. And I'm going to think about this parameter as being OR here, little or, and then I'm going to run the model again, but with different values of this little or. And I'm going to assume that we can control this little or by controlling, for example, how much people move around and meet other people. And then you can see that these different projections, so if OR was 80% of the baseline, then you can see we've flattened the curve, if you like, in the top left. So the peak is pushed later in time and it's smaller. And if I reduced OR to, say, 40%, you can see that I've really flattened the curve in the bottom left figure. And if I reduced OR to 20% of its baseline value, then I could stall the epidemic and eventually the infectious disease would die out. Again, there's quite a lot in these figures and I can't go into all the details now. So it's very much just an illustration of hopefully of how mathematical models can be useful in particular problems. And then you can do similar things with vaccination. So if you had a vaccine that was a perfect vaccine, so if you had the vaccine, then you could no longer transmit the infectious disease, then this simulation would be appropriate. Of course, we know that's not the case for COVID-19 vaccines currently, but in these simulations, that's the assumption. And you can then explore what percentage of the population would need to be vaccinated in order, again, for the epidemic to die out. So the top left figure says that if the vaccination coverage was 50%, then you wouldn't actually stop the epidemic. You would just flatten the curve again. You would push the peak later in time to about day 150. But actually, in the top left figure, the red line is still going above the dashed line. So you're still actually hitting that threshold that you want to avoid. So these results from this very simple model would say that you need to get to 70 or 80%-ish vaccine coverage in order to stall your epidemic. So you can see in the bottom right figure that the red line is tending to 0 by about day 150. So these are very much, as I said, explorations, the real models that people use to inform government policy throughout the COVID-19 crisis. Are more complicated, they have more variables, they account for more detail, but the essence of those models is quite similar to what you're seeing in front of you. So this figure is, or this slide rather, is really trying to kind of broaden out again now and say, well, actually, I could have chosen lots of different topics in order to give you a similar idea about what the usefulness of applied mathematics can be. So I could have picked this graph on the bottom right and said, well, this is a stock price that's kind of changing in time. I could develop a mathematical model, a bit like what we did for the infectious disease, modelling, but I could develop a similar type of mathematical model and use that to study a financial market. Or the top figure in the middle is an image of the sun, a big yellow glowing ball. So I could write down a mathematical model that describes physical processes in the sun and use that to try and understand phenomena such as solar flares or the solar wind. So I can keep giving examples, but I'm not going to. And the key thing is that there are some kind of equations in the middle here, and we've seen some equations to describe the SIOR model. And the key thing is that the symbols look similar in those equations. And in a mathematics degree, one learns how to kind of manipulate these symbols mathematically and understand what they represent. But once you've, as I said at the start, once you've learned the language, then you can apply that language quite freely across different problems. And I think that's really one of the powers of mathematics. Okay, so let's move onwards. I'm just going to quickly check if we have any questions I can help with. Have a little. Okay, so I can't see anything there just now. If you have any questions, so please use the Q&A, and one of my colleagues will be able to help as I'm speaking, or I'll be able to come back to your question when I have a little break in a bit. But if we don't have anything, I'll move onwards. Okay, so that's the end of why mathematics. So let's move on to why mathematics at Dundee. So at Dundee, we have a balance of pure and real-world mathematics. So in order to study these kind of exciting problems that I've just hopefully tried to describe for you, then one needs to have a kind of solid core of the workings of mathematics. And in an undergraduate degree, of course, you learn about that core knowledge, and you also learn then to apply it, in different types of scenarios, which is more what I focused on to date. And of course, in pure mathematics, one studies mathematical objects and mathematical structures, and it's a good thing to study those objects and structures just in their own rights, just for the sake of studying mathematics, because it's interesting and useful. And then one kind of uses that knowledge always when one applies mathematics to particular situations. So our program then has a balance of this development of the core machinery of mathematics, and then thinking about how we can apply it. Our program is informed by world-leading research. So the last time the UK government did its review of research across the UK, Dundee was first in Scotland and 8th in the UK. So that exercise is called the REF, the Research Excellence Framework. And we're very, very proud of that result. We've got a strong focus on employability. We've got small year groups, and we offer an individual experience, and I'll expand a little bit more about that in the next slide. And our program is approved by the IMA. So this is a really useful website, actually, just in general, if you're interested in mathematics. So it's the Institute for Mathematics and its Applications. So I'd strongly recommend that if you find anything that I've said so far interesting, then go to the IMA's webpage, and they've got a lot more info on maths careers and what one can do with it, with mathematical skills. And what I didn't mention here was that Dundee mathematics at Dundee is also 15th currently in the Complete University Guide across all the mathematics departments or divisions in the UK. So quite high in that league table. And one of the things that we take pride in is that we offer a personal learning experience. So we've got an open door policy. Obviously, this year has been an exceptional year, and we've been working at home like most other people. But when we get back to normal routine, we have an open door policy, which means that students are free and welcome to drop into staff offices if they want to discuss, aspects of a module that they might be taking. We've got drop-in help sessions. So every week during the semester, there'll be a couple of timetabled hours where students are invited to come along to speak with someone. It might be a PhD student or a staff member, and they can really bring along any mathematical question that they might have and discuss that. It's called the Maths Cafe. Every student has got an advisor of studies. So the advisor of studies is your kind of point of contact amongst staff, and that it's your advisor's job to help you, for example, to think about your subject choices for the following year, or maybe write a reference for you whenever you've graduated. or if you're having any trouble, then to try and be a person that you can come to get help, or to help you to navigate the university's kind of various support services. So a really important role in your kind of journey through through the university. We offer summer internships in the department. So every summer there'll be a handful of students who are kind of working on research projects for a few weeks to give them a sample of how that works. And we've got a friendly, very friendly and very active math society. So there's just some information on MathSoc. So they organise various events throughout the year, with special focus on induction events, so for new students, and also the annual Maths Ball. This is a still shot. I don't think I'll play the video. Well, this wasn't from last year, but the year before. So usually we have a ceilidh and a night out for students and some staff, and it's quite good fun, involving dancing, mathematicians dancing. Okay, so let's move on. I guess the serious point there is that there is a really supportive community, and I think our students really benefit from that. So just to give you a bit of a feel, again, it's a shame that we're not all meeting face to face on campus, but this is just to give you an idea of where the campus sits relative to the centre of Dundee, and the take home is that it's right in the city centre, and that the campus itself is compact, and that all the places you need to go as a student in terms of lectures, tutorials, meeting staff members, and so on, is all within a few minutes walk. So that's a kind of a magnified shot of the various buildings you might be going to as let's say, a first-year undergrad. Okay, so I think I'll move on now to some more kind of detail about the workings of some of the programs, what kind of programs that we offer. Before I do that, again, I'll try and just give you a chance. If you have a question, I am here to answer your questions, and maybe I'll just stop speaking for a second, and if you have any questions, give you a chance to type them into the Q&A box. All right, so I'll move onwards then. So we're now going to get into a little bit more detail about the kind of programs we have. So you can see this list in front of you. You can also find all these, of course, on UCAS main page if you search for Dundee Mathematics. And I guess the take home is that we offer single honours mathematics, so a BSc and an MMath integrated master's degree. But we also offer joint honours degrees, so mathematics with a whole list of possibilities. So, for example, biology, physics, economics, accountancy, astrophysics, and so on, psychology, English. And I've mentioned that you can exit with a BSc degree or an MMath degree. So let me perhaps use a little graphic to help you kind of see what that means. So basically, as you can see in front of you, that if you exit at what we call level 4, then that would be a Bachelor of Science degree, so a BSc. And if you exit at level 5, so that would be an extra year, then that would be an MMath or an MSci if it was maths with another subject. And then in terms of where you would enter the university, if you were to come here to study mathematics, then you could enter at level 1 or at level 2. So that depends upon your previous experience of mathematics and how you've done. So again, you can probably see this on UCAS. So the entry qualifications are higher for level 2 than they are for level 1 direct entry. And this is something that, again, you could I'm happy to discuss over email if you have any particular queries that you'd like me to help with. But the take home is you could come at level 1 and exit at level 4. You could come at level 1 and exit at level 5. You could come in at level 2 and exit at level 4. So just at different points for entry and exit. So what tends to happen then, and again, the past year has not really been representative, hopefully, of what the future is going to look like, or certainly what's happened before. So just to give you a feel for how things work, so at level 1, if you were to come here at level 1 in a typical year, then you would do a core maths module called Maths 1A, and that's really developing, this core maths, your knowledge of the core maths machinery, so things like calculus, algebra, and building that up. And then you would do a module called Topics in Pure Mathematics. So that's, as I mentioned earlier, we've got real world and pure. It's a way to think about dividing things up. So this module would be on the pure side, looking at various aspects of pure mathematics. And the way our system's structured, then one would also do a non-mathematics module. So that would be a module from another subject at level 1. So this is for a student on a single honours BSc degree. Obviously, if you're doing a joint honours, then you have a mix of modules from maths and whatever the subject is on your joint honours. One can expect 12 to 18 contact hours per week in level 1. And then if you were a BSc mathematics student at level 3, then you wouldn't be doing a non-mathematics module. All your modules will be mathematics, as you can see. And then in each module, one would expect lecture content and then continuous assessment, so quizzes and tests throughout the semester, and then usually an exam at the end of the semester. So a mix of tests throughout the semester and a big exam at the end. I want to say something else about I'll say about that in a second. But we do integrate the use of computational tools, as I'm about to speak in a little bit more detail about, throughout the different levels and the different modules, because we really want, when people exit our various degrees, that they're able to both kind of understand maths and also apply it. And one of the main ways we apply mathematics to real world problems is using computing. So using computers to help us solve problems. So we try and integrate various kind of techniques to do that in various different modules. So perhaps I can have another little break from me, just speaking about aspects of the kind of undergrad program, and I can try and give a little demo of something we do in one of our level 2 modules that almost all of our students do. So I apologise, I've got to good. So now hopefully you can see some squiggly graphs. Just run this thing. Okay, so at level 2 our students do this module called Computer Algebra and Dynamical Systems. And it's just an example of one of the, that's going to be a problem. It wants to show things in a window that you cannot see. Hold on. Bear with me. Oh, wrong one. Sorry, I haven't actually tried to do a live demo with this thing before, hence the rather clunky switch over there. Okay, so I just wanted to kind of show how you can use this package Maple to help you visualize mathematics and do computations. So here we're looking at this idea of tangent to the graph of a function at a particular point. So you can see the function I'm looking at is fx equals sine x. So this, I thought I'd just pick out some topics here that you may have seen already, or you may have seen in the near future. You may see in the near future in school. So we're thinking here about secants, so straight lines joining 2 points in a curve on the graph of a function, and then we're thinking about the limit of the x value of those 2 points getting close together, and how that the line you get is a tangent to the curve at that point. So we're getting, this is a step towards thinking about differentiation in calculus. But what I want to demonstrate here, the details aren't actually that important. What I want to demonstrate is that you can use these packages like Maple to kind of help you do this in really nice ways. So the function we're looking at is sine x. So hopefully you can recognize sine x as the red kind of wave that's graphed. And at x equals 1, I'm going to think about the tangent to the graph of fx equals sine x. So that's this point. And what I'm going to do then is to look at these different sequence of straight lines connecting 2 points on the curve. So one point is always x equals 1, which is over here. And then I'm going to vary this other point. And the idea is that as you get closer and closer to x equals 1, then the line becomes the tangent to the curve. And this is an important concept in thinking about differentiation. And one of the nice things about something like Maple is that, of course, you can easily then, change things. So here we're looking at the same idea, except I've changed the function to tan x. So again, I'll kind of play this forward, and we're playing the same game. And eventually, you can see that as these 2 points on the x-axis, as the second one tends to x equals 1, then this straight line is the tangent to the graph of tan x. So let me close that and hope the next exercise pops up for you. Has it? Not quite. Oh. So bear with me again. This was not what I had anticipated. We'll do one more because this was a bit clunkier than I had in mind. But here we're going to play a similar game. We're going to use this piece of software called Maple to think about limits. So again, I'm thinking about the function sine x, and again, I'm just choosing x equals 1, and I'm using this software Maple to help me compute the limit of fx equals to sine x at x equals 1, which is just here. So let me display this. So you can see then that as we tend to x equals 1, I'm evaluating the graph at different x values. So these are the x values on this column, and these are the y values. And why don't I choose something that's a bit nicer? So why don't I evaluate that at pi? Maybe we all know that, or maybe you may not have seen it before actually, but well, sine of pi is going to be 0. So that's this point here. All right, so I can use the software. And of course, in this case, I know the answer, but I could use it to study an arbitrary function and to study, the limits of an arbitrary function. So again, hopefully you can see how this kind of piece of software, Maple, allows one to really kind of bring mathematics to life, really, and to start exploring things and be able to vary parameters. So, for example, the point you want to evaluate the limit at, and see things that perhaps one couldn't before. So I'll just close that, and I've realized that my demos are just a little bit non-intuitive to show. So let's go back to the slides. Okay, so the take home there, albeit clunkily delivered, apologies for that, was that you can use a software package like Maple, and that's something that you would look at in level 2 with us, as I mentioned, but you can use that to help you explore mathematics, perhaps in ways you haven't done before. Now, the examples I've shown you are concepts that, as I said, you've either seen before or you'll probably see soon. But of course, one can use Maple to study a whole bunch of different things, and I've just chosen those because I thought you might recognize them. So Maple is a really powerful package that one can help to kind of develop a better intuition about various areas of mathematics. But throughout the program, our students also are exposed to different programming languages. So we have a number of stats modules at level 1 and level 2, and students there use a language called OR. And we also have many students do an introduction to programming module, which uses Python, and our students also use another language called MATLAB. So these are all really useful tools, I think, to have as you leave as you graduate, and be able to kind of apply then, whatever you would do afterwards. So being able to solve problems with computer code is a really useful skill to have. Okay, so let's move on. final thing that I wanted to point out was that at the end of our degree at level 4, our students do an honours project. So it's a 30 credit module, so it's worth 2 kind of taught modules, more standard modules, and it's a really interesting, I think, endpoint to the degree where you really get to see how students can apply the knowledge that they've gained throughout their maths degree to various different problems. So you can see here an example of some of the projects that we offer. So that first image is a piece of art called Print Gallery by MC Escher. And there are some mathematical concepts underpinning some of the work of Escher, actually related to an area of mathematics called complex analysis. So in this project, the student explores that idea in a lot more detail. And then the image at the bottom is a Lorentz attractor. So it's an example of a chaotic system. So you can study differential equations, and in particular, differential equations have these chaotic solutions. A lot of relatively recent mathematical work has gone into understanding what this means. I'm not going to say anything more about it today. But you can we also have projects on financial mathematics, on mathematical modelling of brain tumour growth, and so on. Okay, so yeah, that was really the last point on this section. I guess I want to kind of finish off really by looking at some graduate testimonies, and just to let you know where some of our graduates have gone and what they have to say about studying here. So this was Kaylee. I was actually Kaylee's honours project supervisor, and she's gone on to work as a trainee actuary in one of the big actuary firms, and she had an enjoyable time here. Jonas was a joint honours student, maths and physics. He's gone on to work at a very prestigious research institute called ETH Zurich. Again, Jonas comments on the class size, as I mentioned at the start, allowing for a kind of personal interactions with module leaders and so on. And Jonathan, from a few years back, has gone on to work in the oil and gas industry. And again, these are just examples of one of the first points I made, which was this diversity of application areas for mathematics. Well, I haven't got a photo for a very recent graduate who's gone on to work for a logistics firm in Edinburgh. But again, just highlighting the supportive environment and various opportunities like summer internships that the student benefited from and appreciated. So I'll give you a second to read that. Okay, so just a few further points that I perhaps will highlight before I finish up for today. Let me also just check. Yeah, okay, so we don't seem to have any questions just now. Yeah, so in mathematics at Dundee, just to highlight, we've got these flexible degree pathways. So by that I mean that if you were to come to Dundee on a joint honours degree, but you decided after 1 year that joint honours really wasn't for you and you wanted to do one of those disciplines, then we try and facilitate these kinds of changes as best we can. So you're not completely tied to the joint degree if it turns out that it's not optimal for you. So there's flexibility in the system there. What I didn't mention was that in a given module, we have this split usually between lecture content and then workshops and tutorials, computer practicals. So the lecture content is usually the core material that's been delivered, and then the other activities kind of support the learning of that core material and the application. And I mentioned some of the other points before about drop-in help sessions. So that was Maths Cafe and the open door policy. The different variety of assessments, so continuous assessment to encourage kind of work throughout the semester, and then usually a final exam in many modules. I mentioned summer internships, so opportunities to work on different projects throughout the summer, and of course there are study abroad opportunities too. And every year a handful of students will go off to various countries and spend a semester studying abroad. And I will leave it there for today. So thanks very much for your attention. If you have any questions, I'm very happy to take them. I'll be here for the next few minutes, so please post if you'd like to do that. And if you just want to email me, remember my email address is pmurray@dundee.ac.uk.